Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about the vertical oscillations. So, let us consider a string which is attached at the point A. So, this is an elastic string attached at the point A and natural length A. By natural length I mean that it is not yet stretched. Then you add a mass to it. So, it becomes a bit stretched and this is the mass, say m. This is the point A, this is the point B. And this system is in equilibrium. So, there will be a tension say T0 and there will be a force due to gravity mg. So, in the equilibrium position this tension must be equal to this mg. Now, there is something called Hooke's law. Hooke's law tells you that the tension in the string will be increase in length divided by original length. So, if we assume that after you have hung the mass, this length has become b. So, basically if I say this point is O, so this is from this is increase in length divided by original length and there is a lambda and this lambda is called modulus of elasticity. So, this is lambda times increase in length which is AO minus AB because the increase is this much divided by original length which is AB. So, this is equal to lambda times B minus A divided by A and that is your T0. Now, once you have this setup, what you will do is, this is say O, you pull the string up to the point D and let it go. So, this elastic string is going to oscillate just like this. And if I say that P be the position at any time t such that this OP is equal to some x. So, this length is A, this length is B. So, this is the first one where we have only the natural length of the string. This is the second one where we have attached a mass m and we saw what is the tension in the equilibrium position, and this is the third one where you have pulled it till the point D and let it go and it is just oscillating. So, what will be the equation of motion? So, the equation of motion will start with m d2x dt square and you have pulled it in this direction where there is mg and there will be a tension T. And this tension is different from the equilibrium position now because this is now the equilibrium is disturbed and T is the tension which now depends on this x. So, in this direction the force is mg, in the upward direction the force is tension. So, this is our equation of motion. So, why this mg is taken positive and t is negative? Because I have pulled the string in this direction. So, in the direction of increasing x. So, that is why I have to take all the force in this direction to be positive and against this direction to be negative. So, this is in this direction mg, which is positive, and against the direction is the tension, that is negative. Now, if I want to calculate this, let us quickly move to the next page. So, m d2x dt square is equal to mg minus the tension. So, if I want to calculate this one, so let me quickly draw the figure again. So, you have this A, you have this B, you have this O, and you have this D, and this P is the position. So, this length was the natural length A, this is B, this is your X. So, the tension which is acting upwards will be the increase in length by the original length. So, this is equal to mg minus lambda times. So, up to this much is your B and then this much is your X. So, the total length is B plus X minus A, that becomes the increase in length, and divided by the original length, which is your A. So, I can write this is mg minus lambda times B minus A by A minus lambda times X by A. Now, you have already shown that T0, which is equal to mg from here, is equal to lambda times B minus A by A. So, this mg and lambda times B minus A by A, they cancels, and you are left with m d2x dt square is equal to minus lambda times x by A. This is d2x dt square equal to minus lambda times x by A m. So, I can say that this is of the form some minus mu square x. So, the motion is simple harmonic about the center O, and your period of oscillation is 2 pi by root of mu square, which is mu, and your mu is this. So, root of lambda by A m. So, simplifying, I will get 2 pi root of A m by lambda. So, again this vertical oscillation gives you a simple harmonic motion about this center O, and the period of oscillation is this. Let us now modify this a little bit. So, we modify the situation like this, that you have the same kind of scenario. You have B stretched to O at the point D, and let us P be the position. So, this is your A, this is your B, this is your X. So, what I do now is I take this mass, which is somewhere here at the point A, and I drop it. So, if I drop it from the point A, this is going to fall down till to some extent D, and because of the elasticity, again it will move up. But when you have dropped it from this point, from this A to B, this is the natural length of the string. So, till the mass come to the point B, that elasticity is not working. So, it is just a free fall. So, from A to B it is going to be a free fall, and then from B to D you will have a equation of motion which will take care of this tension. So, to model this scenario, what we do is we have from this previous equation, this is your simplified equation of motion. So, if I put this, I will get d2x dt square, that is equal to minus lambda x by am. Now, suppose I put, just for the sake of simplification, this lambda equal to 2 mg. You can do the whole derivation with lambda also, but with this you will have a simplification. So, if I substitute it there, I will get this is equal to minus 2 mg x by am, and so minus 2 g by ax. So, this is our new equation of motion with a particular value of modulus of elasticity. Now, to get the whole scenario about the velocity and the time, we have to solve this differential equation. So, if you want to solve this kind of differential equation, one is using this complementary function and particular integral. However, in this case we have a easy technique. So, all you have to do is multiply both sides by dx dt minus 2g by ax dx dt. Now, this can be written as d dt of dx dt whole square. So, you can see that if I differentiate this, it will be 2 dx dt, and if I differentiate inside, d2x dt square. So, basically you are getting back this, and this side we keep it as it is, minus 2 times g by ax dx dt. Now, this can be written as d of dx dt whole square with an integration sign equal to minus 2 g by a integration x dx. Now, it is not that you are cancelling this dt and dt from that side. I am not getting into that explanation, but just in the next step, do not write this, and this is integration of d of this, and this is d of x. So, if I integrate this, this becomes dx dt whole square. This is minus 2 g by a x square by 2 plus some constant. This 2 cancels, and you are left with dx dt whole square, which is, sorry, you are multiplying by 2 dx dt. So, here it is 2 dx dt, 2 dx dt. This becomes 4, and you are cancelling with a 2. So, dx dt whole square equal to minus 2 g by a x square plus constant. Quickly I draw the figure because I have to use the initial condition. So, this is your a, this is your b, this part is x. So, you have dropped it from the point A. So, at the point B, so let us see what information you know. You have dropped it from this point A and it has reached the point B. So, what is the velocity of this mass at the point B? Since from A to B, since the natural length is also A, that elastic property is not acting when the particle falls or the mass falls from A to B. Only after it reaches the point A, then that elasticity of the string will start working. So, from A to B it is a free fall. So, if it is a free fall and it starts from the point A, your initial velocity, that is u, equal to 0. So, if your initial velocity is equal to 0, then we know that v square equal to u square plus 2gs or 2gx. So, this will be 0 plus 2g times a. So, your velocity is root of 2ga. It is positive because it is moving in the direction of increasing x. So, I know at the point B the velocity is root of 2ga. So, at the point B I write your dx dt is root of 2ga, and then what the value of this x. Now, if you want to calculate this value of x, then we have this T0 equal to mg. Now, we have shown that this T0 is lambda times b minus a divided by a, and this is equal to mg. But we have taken this lambda equal to 2 mg. So, if I substitute it here, I will get 2 mg into b minus a by a equal to mg. So, this mg and mg cancels, and u b minus a becomes a by 2. So, b minus a is this part, and that value is a by 2. So, now if your particle is at the point B and you want to calculate, because x is this distance, but your x has been calculated from this point and it is moving towards this point. So, from O in the downward direction you have calculated the x. However, if you want to calculate the x in the upward direction, I will get the distance, that is from O to B the distance is a by 2, but since it is in the opposite direction, this x is going to be minus a by 2. So, one more time, what is happening is that you have calculated this x from the point O and it is moving in the downward direction, and that direction is taken to be positive in the direction of increasing x. However, if you want to calculate this x again from the point O in the upward direction, it is fine, you will get the value which is from O to B it is a by 2, but since it is moving in the upward direction and not in the downward direction, this we have to consider as minus a by 2. So, our initial condition is that at the point B your dx dt is square root of 2ga and your x is minus a by 2. You substitute it here and you calculate the value of the constant. And if I substitute it here and calculate the value of the constant, I will get this as 2ga equal to minus g by a, x square is a square by 4 plus the constant. So, the constant value is equal to 2ga plus 2g by a into a square by 4, this cancels, this cancels. So, ga by 2, so it is 5ga by 2, and we put it back this here and I get dx dt is equal to square minus 2g by a x square plus 5ga by 2. Now, if I want to find what is the greatest extension. So, the greatest extension is that from this point A you have dropped it and the string has come up to this point where your velocity becomes 0. So, that is the greatest extension, and then move up. So, if I want to calculate this whole value, your value of x, that means I have to put at the point D dx dt equal to 0. So, because it has started from the A and it has come up to the point D. So, to get this much length, I have to put at the D the value is 0 and I calculate that particular x. So, if I put dx dt equal to 0, will give me x square equal to 5 a square by 4, and you will get your x is equal to root 5 a by 2. So, the greatest extension is that from the point B up to the point D. So, BD is your greatest extension, and that is equal to BO plus OD. Now, BO you have already calculated, it is a by 2, and OD you just calculated, which is root 5 by a by 2, and the total extension becomes root 5 by 1 by 2 times a. So, one more time, the greatest extension means that you have dropped it from the point A, and then this mass will fall like this. At this point, the elasticity of the string will come into action, it will go down against, there is a tension, and at one point that tension will be equal to the force, which is mg, and then it will stop. So, it means the velocity will be equal to 0. So, in the velocity equation, you put that equal to 0 like here and calculate the value of x. So, that x is gives you this much value, and this is the extension due to the mass. So, this plus this will give you the greatest extension, which is BO plus OD, and you got this value. Next, if you want to consider how much time it will take from falling here up to the point this. So, if you want to do that, so basically you have a time t1, which is time from B to D. Let me quickly again draw the figure. This is A, this is B, this is O, and this is T, this is P. This is your A, this is your B, and this is your x, and this much is a by 2. So, if you want to calculate the time, you have to consider the equation dx dt whole square, which is equal to minus 2g x square by a plus 5 ag by 2. And if I simplify this, I will get dx dt equal to root of 2g by a root of 5 by 4a square minus x square. A bit simplification, and you can put it in this form. So, if I want to get the time, that is dt, and say from 0 to t1, this will be root of a by 2g integration dx by root of a square minus x square. So, the time is calculated from B to D. So, from this point up to this point. So, if I now want to put the value of x, so x is calculated from O, but it has started from B. So, if I calculate this distance, it is a by 2, but since it is in the opposite direction, this I have to take minus a by 2. And from here to here, I have already calculated that value, which is root of 5 by 2a. So, if you integrate this, this is going to be a by 2g, and this is just sine inverse x by a, which is root 5 by 2a, and the limits from minus a by 2 to root 5 by 2a. If you substitute this and simplify, you will be getting this to be a by 2g pi by 2 plus sine inverse 1 by root 5. This is a simple one, just substitute the values and you will get this value. Now, what will be the time from A to B? And please remember, from A to B it is just a free fall. So, if T2 is the time from A to B, so there you will use x equal to ut2 plus half g t2 square. So, at the point B, your x is a, initial velocity is 0. So, half g t2 square. So, your t2 square is 2a by g, and your t2 is root of 2a by g. So, your time from A to D is T1 plus T2, where your T1 is this quantity, and your T2 is this quantity. If you want that what will be the time from falling from A to D and back, all you have to do is multiply this time 2 times. Let us now look into the numerical solution of this vertical oscillation. So, we have the equation mx double dot is equal to mg minus t, and from here we derived that x double dot is equal to minus lambda by am into x. Now, we have to solve this equation numerically. Now, as you can see, it is a second order differential equation. So, what we do is we make it a system of first order differential equation. And how to do that? So, you put x dot equal to a variable y, and then y dot. So, if we put y dot, this becomes x double dot, because the dot means you are differentiating with respect to time. So, y dot will be equal to minus lambda by am into x. So, if you simplify this, instead of this y dot, if I now substitute this equation, so y dot from here is x double dot. So, you get x double dot is equal to minus lambda by am into x, which is nothing but this original equation. So, this original equation can be written in the system of as a system of equations, first order equations. And I need an initial condition. So, I take, say, at time t equal to 0, I have dx dt is equal to 0 and x equal to, say, some 11. So, when I say dx dt, which is x dot, which is actually the value of y to be 0. And let us take some numerical values of lambda, a and m. So, we will be using Microsoft Excel to solve this system of first order differential equations. Now, I already have the files open. So, as you can see that you have dx dt equal to y, dy dt is equal to minus lambda x divided by am. We have taken lambda equal to 2, a equal to 10, m equal to 20, and the h, which we will be using for Euler's numerical method, is 1. So, I have my t, I have my x, and I have my y. So, at t equal to 0, the value of x is taken to be 11, and the value of y, which is from here dx dt, is 0. So, the velocity at time t equal to 0, y, which is dx dt, that is the velocity is 0, and the initial value of the distance x is 11. So, let us now calculate. So, this is equal to 0 plus 1, and let me drag them. So, the reason we are taking so many values, because there will be an oscillation, and when you take more values, the oscillations becomes much clear. So, we take 400 of these values. Next, we calculate this x. So, x is equal to, so we are solving this is equation, this is equal to x0 plus h which is a constant multiplied by y. Similarly, we calculate y. This is equal to y0 plus h, which is a constant. So we insert the dollar sign multiplied by minus lambda divided by a multiplied by m. And since these are constants, we put the dollar inside, put this thing under a bracket, the denominator, and closed. So this is multiplied by x, that is 11. And now we just drag them to 400 values like this. So I select them, I make the data, the font size a little bit large. We generally take them as 20 and align them. So this is now the calculated value. So let's first plot between t and x. So we will be plotting two graphs, once with t and x, another is between t and y. And we have sort of 400 values. Here. And we go to insert, have the charts, and have the oscillation. So this is one graph. The another one is between t and y. Now to select the third column, what you do is you press Control, you highlight this, you press Shift and the down key. So it will select all the values, and then again you go to Insert and the graph. So the conclusion is that now this one is of x, that is x is equal to y, and this one is the graph for y. So ultimately if I substitute y, this is d2x dx square. So this is basically the velocity and this is basically the distance which you solve from here. And both the curves are periodic in nature, which confirms that there is a vertical oscillation. So with this we come to the end of the discussion of this particular problem about the vertical oscillations. In our next lecture, we will be talking about some epidemic models. Till then, bye bye.